fall out halfway through. Okay. All right, so for our last section, we did a definite integral problem for the warm-up yesterday, right? We had that weird problem that had like the f of 2x plus 3 or whatever was on the inside there. So whenever we did that problem, I did not change my limits of integration. I just put, remember I said, like, we're going to say this is x equals 2 and x equals 4, and we wrote x equals, and you guys really weren't doing that because you didn't know to do that you needed x equals. But we actually, when we have a definite integral, can change our limits, and we'll never have to go back to u. So it makes it a little bit easier, or never have to go back to the x's. So it makes it a little bit easier. So when we have a function that we are integrating, this is just a problem that we would need to use u substitution on. The inside part right here, the g of x, is going to be our u, right? Our u is going to be whatever g of x is, and then our du is going to be g prime of x dx. Right? So like this part is our u. This part right here is our du. So we're going to like switch this where we are integrating f of u du, whatever function we might have. So what we can do is we can take this limit right here, our a, and we can plug it in right here to g, and then we can put that here as our lower limit. If you do this, if you adjust your limits, you don't ever have to go back to x's. Now you've got a u value right there. And then we can do the same thing with our upper limit. We're going to take the b, we're going to plug it into our g of x, and then we're going to use that number up here. And if you integrate this way, everything is in terms of u, and you don't ever have to put the x's back in. Okay, so let's look at an example. I think it's more helpful to see an example than it is to look at all these symbols right here. So, yeah, that's right. Make sure I didn't do one that's too hard. We got some harder ones coming up here in a second, but I've got them in the right order.
Why would you want to do this? Like, what's wrong with substitute x?
Nothing. It's just faster, really. It's faster. So you can substitute the x's back in. I will show you, like, if you do that, you have to be really careful with your notation along the way. Also, there's going to be probably at least one multiple choice problem where they say, evaluate this. And then they don't give the answers. They give the integral adjusted for u's. They'll say, like, for this, let u equal x squared plus 1. They'll even tell you what u is. And then their answer choices are going to be like the integral from 2 to 3 of f of u du. So the answer is not, they've not gone all the way to the answer. So you have to know what they've done there. So in this case, what does it look like we should use for our u? I would go with x squared plus 1 right here. So u equals x squared plus 1. And that means du is going to be 2x dx. Do I have everything I need for my du? I do not. What am I missing? 2. I'm missing the 2. So I'm just going to take the 2 right here, sort of squeeze it in right there, which is okay, as long as I also put a 1/2 out front. So this stuff right here, like that together, we can move that over there, right? Move that over here. That part is our du. So I'm not going to mess with limits right now. I'm just going to rewrite this. I have got the integral from integral of u cubed, and then the 2x dx is my du. Simplifies it a lot right there, right? All of this is just like we were doing on the stuff we've done before.
So what half carries over?
Oh, yes. I've lost my 1/2. Thank you. Okay. Now, if I write 0 and 1 right here, 0 and 1 were here whenever I had a dx, correct? So if I write 0 and 1 right here, I have to put x equals 0 and x equals 1. And then I have to go all the way back and I have to plug the x's back in, and I'll evaluate it from 0 to 1. Okay? It's an option. It works. But if you do it, you have to put x equals 0 and x equals 1. Because if I just put a number right here, and I've got a du over on the end, it is assumed that those numbers are u's. So it would be incorrect on this step to put a 0 and a 1 here, unless you put x equals 0 and x equals 1 up there at the top. But my life is going to be easier if I adjust my limits here. Because if I adjust my limits to make these u's instead, I don't ever have to put the x's back in, which makes the equation so much more simple, right? So what I'm going to do is I'm going to take this bottom limit right here and take 0. I'm going to plug it in right here. So u equals 0 squared plus 1, which gives me 1. And I'm going to put that right here. So that lower limit is 1. And that's a u equals 1. You don't have to write u equals because it's assumed that if you have a du over here and a number right here that doesn't say anything else, that is a u. And then we're going to do the same thing with this top limit right here. We're going to take that 1, we're going to plug it in. All right? That's going to be u equals 1 squared plus 1. That's going to give me 2. That's going to go up here as my upper limit. So I'm going to make myself a note over here. If you change limits of integration you never go back to x's. It's something we could have done on that problem that we did yesterday. We hadn't been there yet, so I didn't encourage it. All right, so all we have to do is integrate. Here, the 1/2 stays out front. I'm going to integrate, so I have u to the 4th power, and then I divide out front by the 1/4. And I don't put a plus c here. Instead, I've got my bracket with the 1 and the 2 telling me how to evaluate this one, because this one is a definite integral. So then I'm just going to plug in my 2, plug in my 1, subtract those, right? So I'm going to leave. You can multiply the 1/2 and the 1/4 together, or you can leave the 1/2 out front. I think I'll multiply them together. I'll get 1/8, and then I'll have 2 to the 4th minus 1/8 times 1 to the 4th. It might be helpful if I write that. Alright, so we're just plugging in 2 and then subtracting what we get when we plug in 1. And then so if it's FRQ, you could, oh gosh, I forgot. I can't scroll down here. If it's FRQ, you could stop there. You're done, but let's simplify it because it might not be on an FRQ. So I've got 1/8 times, that's going to be 16 minus just 1/8. So that is going to, 8, not 18. And that is going to be 2 minus 1/8, which is going to be 16 over 8 minus 1 over 8, which will give us 15 over 8 for our answer. If you plug your x's back in, then you've got like a more complicated equation. You got to do 1/4 times x squared plus 1 to the 4th, and you got to plug those numbers in. So this is going to save you some time by doing this. Any questions here? All right. 2 we actually don't have to do because I just did this on today's warm-up. So this is on your warm-up. Day 4, we're on 4 today. We did this on warm-up day 4. So I want you to think about what you did on the warm-up today. And look at this problem over here next to it. And tell me, what difference do you see? Got this x out front. So you really don't have much of a choice on this one, but to make the u right here the 2x minus 1, just like we did on the warm-up. And so if we do that, the du is just 2dx, just like it was on the warm-up. So just like on the warm-up, I don't have a 2. So I could put the 2 right here, as long as I put a 1/2 out front, and then I've got this part right here is my du. But here is the problem. Like I've set everything up like I did on the warm-up. If I replace everything that can be replaced, I've got the 1/2 right here. I've got the integral symbol. Can I replace that x? It's still there right now. I've got the square root of u du. Can I integrate with respect to u while I still have an x right here? I cannot. This x has to go somewhere, but it's not part of the du, so it's not going anywhere that way. I can't pull it out because it's a variable. If it was a coefficient, that'd be fine. We could pull it out. But it's a variable. We cannot pull variables outside of an integral. What do you mean by that? Not the same. It's not the same base, right? Like it's not the same letter, so we can't like put the x and the u together. So that would be, and we can't. Oh, I see what you're saying. Like break it into one limit here and another, or not limit, one integral here and one over here. That'd be fine if it was addition. If we had like a plus sign in between, that would be exactly what we want to do. In fact, we probably want to do it before we started the u substitution, but can't do that here with multiplication. That doesn't apply to multiplication. Oh, I like that. So if I look up here, I know that u equals 2x minus 1. I got a lot of y'all, on the computers back there. I hope y'all know what you're doing here. It's not going to be easy. U equals 2x minus 1. So that's like a fact that we have set forth. So we can rearrange that formula, right? So I can go up here, and I can say, well, if u equals 2x minus 1, I could add the 1 to both sides. So I've got u plus 1 equals 2x. And I could divide by 2 on both sides. And now u plus 1 over 2 equals x. So this has to be true, right? So I can take that and I can put it over here where the x is at. Now it's not very friendly, but it can happen, right? So I've got 1/2 integral of u plus 1 over 2. Is it okay with you guys if I change u, the square root of u, to u to the 1/2. And I'm even going to do this. When I've got fractions involved, I like to make everything a fraction so I can keep track of where everything's at, right? So the only thing in the denominator right now is that 2. Are we okay here? All right, now if I multiply all this stuff together, I've just got a 2 in the bottom, right? So can I think of that? That's like I got 1/2 integral. Can I write it this way? 1/2 times u plus 1 times u to the 1/2 du, like all this stuff over 1. Is that okay? Like if I multiply that back, would it give me the same thing? It would, right? Like I put these back together, I got u plus 1 over 2. What could I do? That's helpful because what can I do with this 1/2 right here? Now that can be pulled out, right? Because that is just a coefficient. So that helps us out a little bit. So now, I'll go back around here. I got 1/4 integral of u plus 1, u to the 1/2 du. It's looking a little better. Do I know how to integrate u plus 1 times u to the 1/2? I don't have like a product rule for integrals, and I'm not going to have one. This is like, these are the most complicated integrals we're going to get to doing by hand. There are some other things you can do that you'll do probably in Calc 2 if you take it, but we are not required to do that here. We only do like the first little bit of Calc 2. So I can't integrate that like it is. What could I do so that I could integrate it? I could just distribute right here. Okay, so if I do that, now I have 1/4 integral of u to the 3/2 plus u to the 1/2. And then I'm going to put some parentheses here because that du is multiplied by both of those. So we want du on the end for both of those. Can I integrate this? That's just power rule, right? I could just use a power rule for that. I'm running out of room. So I got 1/4. I will have u to the 5/2. You guys okay if I just put 2/5 right here? We're doing 1 divided by 5/2, which just flips that 5/2 and gives us 2/5. Hopefully we've done that enough times that that's not throwing you for too much of a loop. Over here we've got u to the 3/2, and we'll have 2/3 right here. And then we'll have a plus, well, I usually like to end my brackets and put a plus c. And then I'm going to write my answer over here because I ran out of room. We are done. You might see it with the 1/4 left out. They might distribute that 1/4, and they're definitely going to substitute the x's back in because this is not a definite integral. Like your answer needs to be back to x's. So if they distribute, you will have 2 over 20, which is 1/10, times 2x minus 1 to the 5/2. Plus, we'll have 1/4 times 2/3, which will give us 2 over 12, which is 1/6 times 2x minus 1 to the 3/2 plus c. So that would be our answer for this problem. So these problems don't look much different right here at all. It's not immediately obvious that this one's going to be a lot harder. But if you are trying to do UDU substitution and you've got this extra piece that you can't replace that has a variable in it, this is probably what you're going to have to do. You have to convert that x value to a u of some sort. Okay, let's try one that requires that same method and is a definite integral. So we'll practice both of those skills together here. So looking at what we've got here, we've got the integral from 1 to 5 of x over the square root of 2x minus 1 dx. So we're going to have to do a u/du substitution on this one. It's our only method for dealing with difficult integrals, right? If we can't use the power rule, it's the only thing we've got. So what do you guys think the u should be here? It's a 2x minus 1. That's the only thing that would work. So u is going to equal 2x minus 1. I realized the last problem was also 2x minus 1, wasn't it? It's not always 2x minus 1. I picked the same thing here again. And then du would just be 2 dx. So this part right here is my u. I do not have my du, but I could just put a 2 right here. That'd be fine, right? As long as I also put a 1/2 out front. So this part is my du. But much like the last problem, I got this x sitting right here. And it's not replaced yet, right? So I can do like I did on the last problem. I can go over here and say, well, if u equals 2x minus 1, I can add the 1 to both sides. I realize this is a little bit redundant because we just did the same thing, right? And then divide by 2. So u plus 1 over 2 equals x. So this stuff right here, u plus 1 over 2, that can go right here for that x. Now this gets kind of ugly when we start replacing things. All right. For now, let's ignore the limits. Let's not. We're going to work with those here in a second, but let's ignore the limits. Let's just do the integral. In the top right here, I've got u plus 1 over 2. In the bottom, I have the square root of u. And then over here, I've got du. And I lost my 1/2 again, but it should be there. Is everybody okay with where everything came from? This part right here was your x. This piece right here is what we declared as u in the beginning. And this piece right here is your du. Alright, we're going to have to do some work right here, but before we do, now let's worry about the limits, okay? So if I don't want to have to go back to x's, and trust me, you really don't want to have to go back to x's on this problem. If I want to switch to u's and never think about the x's again, then I can adjust my limits here. So what I'm going to do, I wish it gave me more color options for this. I guess I'll just use black. Is I'm taking 1. I'm plugging it in right here to this equation. So u equals 2 times 1 minus 1. Now what do you get for that? Still get 1. It actually didn't change the bottom limit just because of the way that it works. And then we're going to take the 5 and we're going to do 2 times 5 minus 1. It definitely changes the top limit. We're going to get 9 right here. And so 1 and 9 are u values now. We don't have to go back to x's ever, which actually is nice. We don't have to think about that again. But we got to do some work over here because we cannot integrate the way this looks right here. I would probably do this. I'm going to write it as a separate. I would think of it as this. U plus 1 over 2 divided by u to the 1/2 over 1. Alright, that's what we're thinking here. Thinking bubble is very ugly. And whenever I'm dividing fractions, what do? Easy as pie. Flip the second and multiply. So I got 1/2 integral from 1 to 9. All that stays. I'm going to have u plus 1 over 2 times 1 over, yes, u to the 1/2. And du is still there. It is going to be easier right here. I can take this too. I can pull it right out here. I'm going to keep it in the denominator. It's like having a 1/2 out front since that's just a coefficient and the stuff here is multiplied. So now I'm looking at 1/4 integral from 1 to 9 of u plus 1. I'm going to put these back together over u to the 1/2 du. I still can't integrate this. What could I do to get it where I could just use the power rule? I can move it up. So that's going to be 1/4 integral from 1 to 9 of u to the negative 1/2 times u plus 1. And then what can I do with that u to the negative 1/2? Distribute it. So I got 1/4 integral from 1 to 9 of u to the 1/2 plus u to the negative 1/2 du. Whew. All of this just to get to the point where you can actually integrate. All right, let me take a second here, look and see if you have any questions. Okay, so we are going to have to integrate and evaluate now. So I'm coming back over here. 1/4 bracket, increase your exponent by 1, u to the 3/2, divide by the 3/2, so that gives you 2/3, plus u to the positive 1/2, divide by 1/2, that's going to give you 2, and then your brackets from 1 to 9. I think that it is helpful here to rewrite this as square roots before you start plugging numbers in, because fractional exponents are harder to think about. So 1/4, this is going to be 2/3 times the square root of u to the 3rd plus 2 square root of u. Really don't have enough room on this slide, but we can do it maybe. 1/4. I'm going to keep it out front. You could distribute it if you want. I'm going to keep it out front. I'm going to plug in 9. So I got 2/3, the square root of 9 to the 3rd, plus 2 square root of 9, minus, now I need to plug in 1. 2/3, the square root of 1 to the 3rd, plus 2 square root of 1. On the FRQ, you can stop here. You do not have to go any further. However, these show up on the multiple choice sometimes, and you're going to need to simplify that. What I find kids having the most trouble with is this part right here. You've got to do the square root of 9 to the 3rd. What is the square root of 9 to the 3rd going to be? Another little thinking bubble. The square root of 9 to the 3rd. You could do 9 to the 3rd. 9 times 9 times 9. But most likely you're going to number so big that you don't know what the square root of it is anyway, right? This also can be the square root of 9 to the 3rd. We can like switch sort of like the order of the exponents there, because square root is really like a 1/2 exponent. What is the square root of 9? 3. What's 3 to the 3rd? 27. So it makes that doable, where otherwise it's crazy. So 27 plus 2 times 3. You have to be really careful with parentheses here. This is just going to be 2/3 plus 2. So 2/3 of 27 is going to be what? 18 plus 6 minus, oh gosh, so many fractions. 2/3 plus 2 is going to be 2/3 plus 6/3. That's going to be 8/3. Um, 18 plus 6 is going to be 24. We really need to change it so that it's over 3. 24 over 3, or 24, and we're putting it over 3. It's going to be 72. Is that right? That's 3 days. 3 days, 72 hours, right? Minus 8 over 3. Whew. This is getting a little extensive. I have then going to get 64 over 3. 64 and 4 will reduce. What's that, 16? And so finally, I get 16 over 3. Whew. I am afraid to even do this. These need to be calculator inactive. They're going to be in the calculator inactive section of your book. But I'm afraid to even do this at the risk that I miss it. But the Desmos will calculate this. If you want a definite integral, go over to functions. Down towards the bottom, I think, is where calculus is. Where's the definite integral? Why is that not there? Oh, it comes up automatically. 1, 2, 5 x over square root of 2x minus 1 dx. Please tell me that's 16 over 3. So the Desmos will do this for you, but it's not going to be on the calculator active section, so you got to know how to do it by hand. But you can use it to help check as you work through. I think you mostly have odds anyway, but all right. So your assignment is going to be from page 342. So we're going back to. It actually starts on. Yeah, I guess it starts on 342. 63, 65, 67 are going to be these like hard problems that where you got that extra x in them. They are difficult. 69 is so difficult that if you can bring me a paper with it solved out and explain to me what you did, because the answer's in the back of the book, but you've got to show me what you did and be able to tell it to me, because I haven't even tried to see if ChatGPT can do it. But if you don't understand what ChatGPT is giving you, I just got done with test corrections for pre-cal, and not one but 2 students found the derivative and used that to prove where the function was increasing on one of their test corrections. I did not give them credit for that correction. If they can come up to me and explain me what a derivative is, how to find it, and why that's the correct answer, I'll change my mind. But I'm pretty sure they're copying something down from AI that they have no idea what it is. And I don't even mind them using AI, but you need to know, like, I don't know this. This can't be, instead of blindly writing things down, which was obviously happening there. So 69 is not really required at all. And then you've got 71 through 81. Most of those are going to be much more simple. In fact, I know 71 through 79, you do not have to do the extra x part. Like, it's just a regular u substitution. It's just these are definite integrals, which we haven't practiced yet. With the u substitution, you can change your limits to make it a little bit easier. 81, let's put 81 on the extra credit one, too. It's a little bit crazier. We'll put 81 on the extra credit. So, 69 or 81, if you do them on a separate sheet of paper where you can like turn that in to me, where I have time to like look over it and then ask you questions about it. So do those on a separate sheet of paper if you choose to do them. They are not required. So we actually have a few minutes for you to start on this, so that's lovely. If you want to get done what you can get done fastest first, the definite intervals are going to be faster. The 63, 65, and 67 are going to be the longer ones.